Hello everyone, welcome to session 6. So in the last session we have discussed balancing a chemical reaction by two methods, right? For the exam point of view, the first method, that is oxidation number method, is very much important, so you have to study harder. Okay, so now in this session we will discuss application of redox reactions. That means in laboratory you might have conducted this experiment already, that is titration. So actually the titration which we have done in the lab is nothing but sodium hydroxide versus oxalic acid. We have taken sodium hydroxide in burette, we have taken oxalic acid in conical flask, then we released sodium hydroxide drop by drop, then sodium hydroxide reacts with oxalic acid present in the conical flask, then we got some end point, so we determined the concentration of NaOH, right? So that one we have conducted in the laboratory. So that is nothing but a titration, that is sodium hydroxide versus oxalic acid, or it is also an example of acid base titration because it involves acid and base. So generally this acid base titration is nothing but a redox titration. So there is an involvement of redox reaction, so that one we will see. But for your syllabus, okay, in your syllabus they have mentioned two different titrations, that is potassium permanganate versus ferrous ammonium sulphate and potassium permanganate versus oxalic acid. Okay, so we will study how the redox reactions are taking place in this titrations. Okay, so we are not going to see how the redox reaction taking place in these sodium hydroxide and oxalic acid titration. Instead we will see these two examples. Once if you understand this, you can easily solve this. Okay, so first you see here, acid base titrations are nothing but redox reactions. Example, sodium hydroxide versus oxalic acid, which we have conducted in the laboratory. So in addition to this titration, we have other two titrations, that is potassium permanganate versus ferrous ammonium sulphate and potassium permanganate versus oxalic acid in acid medium. So these two are also an example of redox reactions. How? First we will take potassium permanganate versus oxalic acid in acid medium. Okay, so first you have to know the molecular formula of potassium permanganate, that is KMnO4, oxalic acid, that is C2H2O4. Actually that looks like this, COOH COOH. This is the oxalic acid molecular formula. Actually for the exam point of view this is not that much important, okay, but we are discussing since it is there in NCERT, okay, but important for your CET point of view. So now you see here, titration potassium permanganate versus oxalic acid. First we have to set up titration setup like this. So we will be having burette, we will be having conical flask. In burette we will take potassium permanganate, that is KMnO4. In conical flask we will take oxalic acid, that is C2H2O4. Since we are carrying out this experiment in acidic medium, we will add sulfuric acid, that is H2SO4, small amount of sulfuric acid. Now why we do titration? In order to find the concentration of any one solution, okay, any one unknown solution. So we don't know the concentration of potassium permanganate, we know the concentration of oxalic acid, that is standard oxalic acid. So by noting down the end point, we can calculate the concentration of potassium permanganate by using formula, isn't it? So that is our objective. So that and all not needed now. Just we have to see how the redox reaction occurs in titration. Okay. So in this titration we have taken potassium permanganate in the beaker, oxalic acid in the conical flask, and we have added sulfuric acid. So now when you release the drop of potassium permanganate inside conical flask, the potassium permanganate reacts with sulfuric acid which we have added, right? So then it will give nascent oxygen. When potassium permanganate reacts with sulfuric acid, then we will get nascent oxygen or free oxygens. Okay, just you remember like this now. Then the oxalic acid present in the conical flask reacts with this nascent oxygen to give carbon dioxide. This is the main products. Okay. So since the nascent oxygen in the second equation is only 1 and nascent oxygen in the first equation is 5, in order to balance both the equation, I will multiply second equation by 5 so that I will get 5 C2H2O4, 5 nascent oxygens, 5 water molecules, 5 into 2 that is 10 carbon dioxide molecule. So that the overall reaction which occurs in the conical flask is nothing but sum of these two equations. That is, you add this reactant side, you add reactant side, here you add product side, like this, you will get the equation like this. Okay. So in this titration, how we can say redox reaction is taking place? Now you can see. Take this molecule, potassium permanganate. What is the oxidation of manganese here? How can we calculate that? In KMnO4, you have to calculate oxidation state of manganese. Let it be X. I am going to calculate this. Okay. Then what is the oxidation state of potassium? Potassium always exists as K plus. So oxidation state of potassium is +1 plus X plus oxidation state of oxygen commonly, that is -2. Since there are 4 oxygen atoms, 4 into -2 is equal to overall charge of the atom molecule, that is 0. Overall charge is 0. You solve this, what you will get? X 1 plus X minus 8 is equal to 0. X will be is equal to +7. So oxidation state of manganese in this case is +7. Now you come here. You observe this. What is the oxidation state of manganese here? So in manganese sulphate, okay, let oxidation state of manganese be X. I am going to calculate it now. Plus, what is the oxidation state of sulphate? As we know that sulphate always exists as 2 minus. So sulphate molecule will possess -2 oxidation state. Then overall charge of the sulphate molecule is 0. You solve this equation, X plus into minus 2 is equal to 0 and X will be equal to +2. So here manganese will possess +2 oxidation state. So we can understand that manganese is undergoing reduction. Decrease in the oxidation state from +7 to +2 is nothing but reduction. Okay, so in this reaction we can notice reduction. So come to second reaction. We have oxalic acid in conical flask. This oxalic acid, you calculate the oxidation state of this carbon now. I will erase this first. Come here. We have oxalic acid like this, C2H2O4. What is the oxidation state of carbon here? I have to calculate, I will take X. Since there are 2 carbon atoms, I will take 2X plus oxidation state of hydrogen. Generally hydrogen exhibits +1 oxidation state because hydrogen exists as H plus. So since there are 2 hydrogen atoms are there, I will take 2 into 1 2 plus oxidation state of oxygen is commonly -2. There are 4 oxygen atoms, 4 into -2 and total charge will be equal to 0, isn't it? So now solve this. 2x plus 2 plus into minus 4 into 2 8 is equal to 0. 2x will be equal to 6 and x will be equal to 3. So in this case one carbon atom will possess +3 oxidation state. Now come to this carbon dioxide molecule. So what is the oxidation state of carbon? Let it be X plus commonly oxygen exhibits -2 oxidation state. There are 2 oxygen atoms, 2 into -2 is equal to overall charge, that is 0. Solve this, X plus into minus 4 is equal to 0, X will be equal to +4. So here carbon atom exhibits +4 oxidation state. So in first reaction manganese exhibits +7, here +2, and you can notice the reduction reaction. So in the second equation, chemical reaction, carbon is undergoing oxidation from +3 to +4, isn't it? So in titration we can notice both reduction as well as oxidation reactions. So if we can notice both the reactions, then that is nothing but redox reactions. Okay, so this is the titration. works on the principle of redox reaction, or redox reactions are the basis of titration. Okay, so if I want to summarize in single sentence, I can say, see, oxalic acid present in the conical flask reacts with nascent oxygen. So where we will get nascent oxygen? From where we will get? From first reaction. How we got this? Because manganese reacts with sulfuric acid. Okay, so this is how you can understand this. So here potassium manganese undergoes reduction, oxalic undergoes oxidation. Okay, so if you have any doubt, you can comment, ask me. So you can understand this overall reaction as well. And at last, the ionic equation for the above equation is nothing but this one. So ionic equation is nothing but, in solution state, potassium permanganate breaks down into permanganate ion. Okay, in solution state, potassium permanganate in solid state we will get like this KMnO4, but in dissolved state, in solution state, we will get that as like this permanganate ion. Sulfuric acid, when we dissolve this in water or some in any solvent, we will get H plus ion. Since it is acidic in nature, that will release H plus ion. So this oxalic acid in solution state, it will break down and it will give oxalate ion. It will give oxalate. This is manganese, water and carbon dioxide. You can understand this. Okay. So now let us move on to another example, that is potassium permanganate versus ferrous ammonium sulphate. So this is another titration. In the same way, potassium permanganate, as you know that is KMnO4. Ferrous ammonium sulphate is nothing but NH4 twice FeSO4 twice dot hexahydrate 6H2O. This is ferrous ammonium sulphate. This is also known as Morse salt. You remember this? Morse salt. Morse salt is nothing but ferrous ammonium sulphate. And in some books you might have observed this. They will write like this: ammonium sulphate, that is NH4 twice SO4 dot ferrous sulphate, that is FeSO4 dot 6H2O hexahydrate. So both are same only. Okay, so it is nothing but Morse salt or ferrous ammonium sulphate. So here same, this titration also involves redox reaction. So first you understand the setup, like potassium permanganate will be taken in what? Burette. In conical flask we will take ferrous ammonium sulphate. Since we are conducting this experiment in acidic medium, we will add small amount of sulfuric acid. Then now we have to find out the concentration of potassium permanganate. We know the concentration of ferrous ammonium sulphate, that is standard solution. So by using mathematical formula, we can calculate this potassium permanganate after getting the end point, after getting the titer value, right? That is the principle. So now that and all not needed. This is the principle, just I have given some introduction to you. So now what happens in the titration reaction? You see, potassium permanganate reacts with sulfuric acid, which is there in the conical flask. So that will give nascent oxygen. Okay. Why nascent oxygen is released? Because permanganate reduces from +7 to +2. Since it is undergoing reduction, it will give oxygen, nascent oxygen. And we also know that reduction is nothing but removal of oxygen also, isn't it? Definition you know. We have another definition for reduction, that is removal of oxygen. So oxygen is removed from this molecule and we will get oxygen, free oxygens like this. So this free oxygen will oxidize this ferrous sulphate, that is nothing but Morse salt. So Morse salt composition is ferrous sulphate and ammonium sulphate dot hexahydrate, isn't it? So in that we will be having ferrous sulphate. more salt, or FAS is nothing but ferrous sulfate, NH4 twice, sulfate dot hexahydrate. So this ferrous ammonium sulfate contains ferrous sulfate. That ferrous sulfate reacts with sulfuric acid and nascent oxygen that is obtained from the first reaction, and it will give ferric sulfate like this. Okay, so in this way that reaction occurs. So now we have to find how redox reaction is taking place here. As we all know, in last slide we have calculated plus 7 to plus 2. So here manganese is undergoing reduction. In this case, calculate the oxidation state of iron. So let it be X plus oxidation state of sulfate is minus 2. SO4 2 minus. Last slide only we have solved that. Okay, that will be equal to overall charge 0. So X will be equal to plus 2. So here iron exhibits plus 2 oxidation state. Come here. So in this case Fe2 SO4 thrice. Let the oxidation state of iron be X. Since there are two iron atoms, 2X plus oxidation state of sulfate. Sulfate exhibits minus 2 oxidation state, so minus 2. Since there are 3 sulfate ions totally, so 3 into minus 2 is equal to overall charge is 0. Solve that, you will get 2x plus into minus minus 3 into 2 6 is equal to 0. 2x is equal to 6, x is equal to plus 3. So here oxidation state of iron, one iron is plus 3. So here iron ion is undergoing oxidation from plus 2 to plus 1. So which is responsible for the oxidation of iron? Nascent oxygen is responsible. So from where we got this nascent oxygen? From the first reaction. Why we got this in the first reaction? Because potassium permanganate is undergoing reduction. Okay, so anyhow, to avoid confusions, we can remember like this. So in titration we can notice both reduction as well as oxidation. So titrations are nothing but redox reactions. Okay, so this is we can write. And you know overall reaction, so you multiply whole equation by pi 5. Why? Because here only one nascent oxygen is there, but here we have 5. In order to balance both the equation, first I will multiply this equation by 5. So we will get 5 into 2, 10, here 5, here 5, here also 5, here also 5. So then add left hand side, add right hand side, you will get the overall equation. Okay, so ionic equation. Ionic equation is nothing but in solution state potassium permanganate exists as permanganate ion, sulfuric acid exists as H plus. Since it is an acid, it will release H plus ions. Ferrous sulfate, that is ferrous ammonium sulfate, will release ferrous ions. So you will get manganese, water and ferric ions. Fe3 plus is nothing but ferric ion. Okay, this is how we can write this. So now you can see manganese undergoes reduction, ferrous undergoes oxidation to become ferric. So this is how, since both reduction and oxidation reactions can be noticed in titration, the titration reactions are what? Redox reactions. So next, now we will discuss direct redox reactions and indirect redox reaction. This might be the last topic of this chapter, and after this we will be having this Daniel cell. We will discuss that. Okay. So what is direct redox reaction? Redox reactions which involves the transfer of electrons from reducing agent to oxidizing agent present in contact with each other. So it is nothing but in titration reaction we observed that in the first reaction electrons will be gained, isn't it? See, in the first reaction manganese reduces from plus 7 to plus 2. Second reaction iron oxidizes from plus 2 to plus 3. So first reaction is reduction. Reduction is nothing but what? Gaining of electron ಅನ್ನು gain ಮಾಡ್ಕೊಳ್ಳುತ್ತೆ. Second reaction is nothing but oxidation is nothing but loss of electrons, isn't it? So this reaction will lose electrons, this reaction will gain electrons, so electrons will be transferred from here to here, isn't it? So from reducing agent to oxidizing agent. So redox reaction which involves the transfer of electrons from reducing agent to oxidizing agent, okay, which are in contact with each other, because we can see in titration these two reactions are in contact with each other in a conical flask. So that is nothing but direct redox reaction. Direct redox reaction means both the electron transfer will occur due to the contactness of both the reactions or both the solutions, I can say. Indirect redox reactions means these are also redox reactions. There also we can notice oxidation and reduction, but indirectly in separate vessel. Okay, not in single conical flask, but in separate vessels we can see that reaction. In one vessel there will be an oxidation, in another vessel there will be an reduction reaction. Okay, so such reactions which occur indirectly are nothing but indirect redox reaction. So you will not understand this unless and until we teach electrochemical cells. So first you remember the definition. Now I will teach electrochemical cells. So the best example where the indirect redox reactions occurs is electrochemical cell. In electrochemical cells we can observe the indirect redox reactions. What are electrochemical cells? Electrochemical cells are nothing but the cells which will convert chemical energy to electrical energy. So these things you will study in second PU. Just now you understand the brief introduction. Okay, so electrochemical cells are nothing but the cells which convert chemical energy to electrical energy. See, for example, in your home you might have observed these battery cells, right? Like this we will be having cell. Do you know we have two size cells? One will be of larger size and another will be of smaller size. This cell you will use in remotes, smaller size one. This one we will use in clock, right? Generally the size of the cell is measured in terms of alphabet. Actually the size of this cell is AAA size and size of this cell is AA size. Minus plus minus plus, isn't it? So what happens inside the cell? Actually there will be an occurrence of chemical reaction. So there will be a production of chemical energy due to the redox reactions. Then this chemical energy will, you will get the chemical energy as electrical energy, isn't it? So this is what happens in the cell. So electrochemical cells are nothing but battery cells only. So now the common electrochemical cell which we are using now is nothing but galvanic cell or voltaic cell. This is the name of the cell. Actually the name why they have given galvanic or voltaic means this is invented or discovered by Luigi Galvani and Alessandro Volta. That is the reason we are giving the name galvanic cell or voltaic cell. Okay, so this the best galvanic cell till today is Daniell cell. Okay, so electrochemical cell, so electrochemical cell, common electrochemical cell are nothing but galvanic cells. The best galvanic cell, example of galvanic cell is Daniell cell. So if we study the Daniell cell we can understand what is indirect redox reactions. So construction and working of Daniell cell, how the Daniell cell looks. See, actually this cell consists two electrodes, two electrolytes, one salt bridge, one voltmeter. Okay, so first of all we have to understand what are electrodes, electrolytes, salt bridge and voltmeter. So with the diagram only we can understand this. So these are the key components in the Daniell cell. So this is the Daniell cell. So here you can see two electrodes. Electrodes are nothing but metallic rods. So here we have one metallic rod, here we have another metallic rod. Okay, these are electrodes. We want two of different metals. Here we have taken zinc rod, here we have taken copper rod. So these zinc rod must be dipped in a solution called as electrolyte. Electrolytes are nothing but solutions, okay, containing ions which are same as that of rod. See, zinc rod contains Zn, isn't it? Zinc. So the solution or the electrolyte which we take to immerse this rod must also should contain the same ions. Okay, so we will take zinc sulfate, because in zinc sulfate we will get zinc ions, Zn2 plus ions. So the rod which we have taken is zinc, and the electrolyte which we have taken contains zinc ions. So the same, these must be same, same. Okay, and in the same way we will take another rod, that is copper rod. So we will dip this rod in a solution which contains copper ions. Okay, so we will take copper sulfate. So when copper sulfate breaks, it will give Cu2, SO4 2 minus and Cu2 plus. So we will get the ions which are same as that of rod. So the construction of Daniell cell involves two electrodes that are rods of different metals and that are dipped in or that are immersed in, those are immersed in electrolyte, that is zinc sulfate and copper sulfate. And there will be an external circuit which is connected to voltmeter to measure the current produced or the voltage produced due to the chemical reaction occurring in the vessels. Okay, and there will be an presence of salt bridge, generally that is made up of potassium chloride. Salt bridge is used to establish a connection between this solution and this solution. Okay, so as you know that circuit means that must be closed circuit. So if there is no closed circuit, then current will not flow. So in order to complete the circuit like this, we will introduce this salt bridge. In the absence of salt bridge, we can't complete the circuit. So salt bridge is introduced to complete the circuit. So this is how Daniell cell is constructed. Okay. So Daniell cell contains zinc rod. I will summarize in 2 minutes. Daniell cell contains zinc rod dipped in zinc sulfate, copper rod dipped in copper sulfate, and both the rods are connected externally with voltmeter, and both the electrolytes are connected internally with salt bridge. So this is the electrochemical cell construction. So in this reaction, the zinc rod is termed as anode. Okay, and the copper rod is termed as cathode. As we indicate plus and minus in the cell, same way the positive terminal, that is copper rod, is positive terminal, zinc rod is negative terminal. So in an electrochemical cell, negative terminal are termed as anode, positive terminal as termed as cathode. So in anode always oxidation occurs, in cathode always reduction occurs. So how can we see that? See here at anode. So at this place what happens is oxidation occurs, isn't it? Oxidation occurs. How? Zinc undergoes oxidation to give electron, 2 electrons. Zinc undergoes oxidation from 0 to +2 by losing 2 electrons. So at cathode, reduction occurs. How reduction occurs? There will be copper 2 plus ions in the solution that will accept electrons and that will give copper like this. So this is how reduction occurs. So in this oral cell, there is an oxidation reaction, there is an reduction reaction, but both are taking place in different vessels. So this is an example of indirect redox reaction. So since there is a production of or involvement of electrons, so electrons will move from here to here. Okay, because in this, I will rub this once again. So here at anode, zinc will produce 2 electrons, isn't it? Zinc will produce electrons, so that electrons will move towards cathode. Okay, since electrons are negatively charged, cathode is positively charged, these electrons will move towards cathode, and at cathode copper 2 plus ions will accept those electrons and will give copper. So in an overall manner we can say electrons are moving from this circuit, this zinc rod to copper rod, and once again they will reach here, so that there is a movement of electron. And in lower classes you might have studied, that is movement of electrons are nothing but current. So if electron moves and there will be a production of current, so that current, the amount of current produced is can be seen using voltmeter. Okay, so this is how what redox reactions are present in an electrochemical cell. This is how the indirect redox reactions can be noticed in electrochemical cell. So now redox couple. What do you mean by redox couple? So having together the oxidized and reduced forms of substance taking part in oxidation or reduction half reactions are nothing but redox couple. So first of all, half reactions means this is oxidation half reactions, in which the container in which only oxidation occurs. So this is oxidation half reactions, and this is the reduction half reaction where only reduction reaction is taking place. Okay, so the products of both the reactions combined together are nothing but redox couple. So the product of both the reaction are nothing but redox couple. So if in exam you write this definition, but practically you have to remember like this. Okay, so the oxidized and reduced forms of a substance, this is the oxidized form of zinc, this is the reduced form of copper, isn't it? So oxidized form of substance and reduced form of substance are called as redox couple. Okay, so then at last we can see what do you mean by electrode potential. Electrode potential is nothing but potential developed when a metal is in equilibrium with solution of its own ions. That means in electrochemical cell we will immerse a rod like zinc in zinc sulphate, isn't it? So electrode potential means the potential developed between these two rod and solution. Okay, when there is an equilibrium between zinc and ions in the solution. ಯಾವಾಗ ಜಿಂಕ್ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಸೊಲ್ಯೂಷನ್ ಇರೋ ಜಿಂಕ್ ಅಯಾನ್ಸ್ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಜೊತೆ ಈಕ್ವಿಲಿಬ್ರಿಯಮ್ ಅಲ್ಲಿ ಇರುತ್ತೆ, ಅಂದರೆ ಎರಡು ಕೂಡ ಆಲ್ಮೋಸ್ಟ್ ಸೇಮ್ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಇರುತ್ತೆ, ಆ ಟೈಮಲ್ಲಿ ಈ ಸೆಲ್ಗೆ ಒಂದು ಪೊಟೆನ್ಷಿಯಲ್ ಡೆವಲಪ್ ಆಗುತ್ತೆ. ಪೊಟೆನ್ಷಿಯಲ್ ಅಂತಂದ್ರೆ ದಟ್ ಒನ್ ವಿ ವಿಲ್ ಡಿಸ್ಕಸ್ ಇನ್ ಸೆಕೆಂಡ್ ಇಯರ್ಸ್. ಓಕೆ, ಆಕ್ಚುಲಿ ದಟ್ ಕಮ್ಸ್ ಅಂಡರ್ ಎಲೆಕ್ಟ್ರೋಕೆಮಿಸ್ಟ್ರಿ. ಸೊ ಏನೋ ಒಂದು ಪೊಟೆನ್ಷಿಯಲ್ ಜನರೇಟ್ ಆಗುತ್ತೆ ಅಥವಾ ಎನರ್ಜಿ ಜನರೇಟ್ ಆಗುತ್ತೆ. ಆ ಎನರ್ಜಿ ಜನರೇಟ್ ಆಗುತ್ತಲ್ಲ ವೆನ್ ದೇರ್ ಇಸ್ ಎನ್ ಎಕ್ಸಿಸ್ಟ್ ಜಿಂಕ್ ಮತ್ತು ಜಿಂಕ್ ಅಯಾನ್ಸ್ ಮಧ್ಯೆ ಈಕ್ವಿಲಿಬ್ರಿಯಂ ಎಸ್ಟಾಬ್ಲಿಷ್ ಆದಾಗ ಏನು ಎನರ್ಜಿ ಡೆವಲಪ್ ಆಗುತ್ತೆ ಆ ಸೆಲ್ಲಲ್ಲಿ, ಆ ಎನರ್ಜಿಯನ್ನು ಎಲೆಕ್ಟ್ರೋಡ್ ಪೊಟೆನ್ಷಿಯಲ್ ಅಂತ ಕರಿತೀವಿ. ದೆನ್ ಸ್ಟ್ಯಾಂಡರ್ಡ್ ಎಲೆಕ್ಟ್ರೋಡ್ ಪೊಟೆನ್ಷಿಯಲ್ ಅಂದರೆ ಏನು ಅಂತಂದರೆ, ಪೊಟೆನ್ಷಿಯಲ್ ಡೆವಲಪ್ ಆಗುತ್ತೆ ಸೆಲ್ಲಲ್ಲಿ ಯಾವಾಗ ಅಂತಂದರೆ ಮೆಟಲ್ ಈಸ್ ಇನ್ ಈಕ್ವಿಲಿಬ್ರಿಯಂ ವಿತ್ 1 molar ಸೊಲ್ಯೂಷನ್ ಆಫ್ ಇಟ್ಸ್ ಓನ್ ಅಯಾನ್. ಯಾವಾಗ ಅಂದರೆ ಮೆಟಲ್ಲು ಜಿಂಕ್ ಸಲ್ಫೇಟಲ್ಲಿ ಡಿಪ್ ಮಾಡಿರ್ತೀರ ಜಿಂಕ್ ಮೆಟಲನ್ನು, or you can say any metal. Okay, copper dipped in copper sulphate. Okay, so ಯಾವಾಗ ಈ ಜಿಂಕ್ ಸಲ್ಫೇಟ್ ನೀವು ಸೊಲ್ಯೂಷನ್ ತಗೊಂಡಿರ್ತೀರಲ್ಲ ಅದರದ್ದು ಕಾನ್ಸಂಟ್ರೇಷನ್ 1 molar ತಗೊಂಡಿರ್ತೀರ, ಈ ಸೆಲ್ಲನ್ನು 298 ಕೆಲ್ವಿನಲ್ಲಿ ಇಟ್ಟಿರ್ತೀರ, ಅಂದರೆ ಅರೌಂಡ್ 25 ಡಿಗ್ರಿ ಸೆಲ್ಸಿಯಸ್ ಅಲ್ಲಿ ಇಟ್ಟಿರ್ತೀರ. ಸೊ ಈ ಕಂಡೀಷನಲ್ಲಿ ಅಟ್ 25 ಡಿಗ್ರಿ ಸೆಲ್ಸಿಯಸ್ ಅಟ್ 1 molar ಕಾನ್ಸಂಟ್ರೇಷನ್ ಆಫ್ ಜಿಂಕ್ ಸಲ್ಫೇಟ್, ಈ ಟೈಮಲ್ಲಿ ಜಿಂಕ್ ಕಾನ್ಸಂಟ್ರೇಷನ್, ಜಿಂಕ್ ರಾಡಲ್ಲಿರೋ ಜಿಂಕ್ ಕಾನ್ಸಂಟ್ರೇಷನ್ನು ಜಿಂಕ್ ಸಲ್ಫೇಟ್ಲಿರೋ ಜಿಂಕ್ Zn2+ ಅಯಾನ್ ಕಾನ್ಸಂಟ್ರೇಷನ್ನು ಎರಡು ಈಕ್ವಿಲಿಬ್ರಿಯಂ ಇದ್ದಾಗ, ಅಂದರೆ ಎರಡರದ್ದು ಕಾನ್ಸಂಟ್ರೇಷನ್ ಸೇಮ್ ಇದ್ದಾಗ ಈ ಸೆಲ್ಗೆ ಒಂದು ಎನರ್ಜಿ ಡೆವಲಪ್ ಆಗುತ್ತೆ, ಪೊಟೆನ್ಷಿಯಲ್ ಡೆವಲಪ್ ಆಗುತ್ತೆ. ಅದನ್ನು ನಾವೇನಂತ ಕರಿತೀವಿ, ಸ್ಟ್ಯಾಂಡರ್ಡ್ ಎಲೆಕ್ಟ್ರೋಡ್ ಪೊಟೆನ್ಷಿಯಲ್ ಅಂತ ಕರಿತೀವಿ. ಸೊ ಎಲೆಕ್ಟ್ರೋಡ್ ಪೊಟೆನ್ಷಿಯಲ್ ಇಸ್ ನಥಿಂಗ್ ಬಟ್ ಎನರ್ಜಿ ಡೆವಲಪ್ಡ್ ಇನ್ ದಿಸ್ ಸೆಲ್ ವೆನ್ ದ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಆಫ್ ಮೆಟಲ್ ಈಸ್ ಇನ್ ಈಕ್ವಿಲಿಬ್ರಿಯಂ ವಿತ್ zinc ions in the electrolyte, isn't it? Standard electrode potential is nothing but that is the equilibrium developed between the zinc and the zinc ions in the electrolyte. But condition ಏನು, ಎಲೆಕ್ಟ್ರೋಲೈಟು ಕಾನ್ಸಂಟ್ರೇಷನ್ 1 molar ಇರಬೇಕು ಮತ್ತು ಸೆಲ್ದು ಟೆಂಪರೇಚರು 25 ಡಿಗ್ರಿ ಸೆಲ್ಸಿಯಸ್ ಅಥವಾ 298 ಕೆಲ್ವಿನ್, ಎರಡು ಒಂದೇ ಇಷ್ಟರಲ್ಲಿ ಇರಬೇಕು. ಈ ಟೈಮಲ್ಲಿ ಏನು ಎನರ್ಜಿ ಡೆವಲಪ್ ಆಗುತ್ತೆ ಸೆಲ್ಗೆ, ದಟ್ ಇಸ್ ನಥಿಂಗ್ ಬಟ್ ಸ್ಟ್ಯಾಂಡರ್ಡ್ ಎಲೆಕ್ಟ್ರೋಡ್ ಪೊಟೆನ್ಷಿಯಲ್. So I hope we discussed everything in this chapter. So by the next session we will start with hydrogen. So we will wind up now. Thank you all.